Yes.
Great. Okay. Can you see my cursor as well?
Yep. Yep.
Fantastic. Okay, so thank you for the invite, Demetrius. I think you're right. I think it was about the week before lockdown that I got a bit scared and decided not to come, which in retrospect was perhaps a good decision. So I'm going to talk about free surface nanoflows. And let me start by mentioning a few potential applications. So it's no specific application that we're looking at really, but there are a number of interesting nanoflows associated with emerging technologies. So this is one we've actually been working on ourselves, and that's the idea that you can remove heat from surfaces, in particular electronics, by droplets coalescing and then jumping from surfaces and taking heat with them. And the idea of this work was to see if nanodrops will jump off surfaces or not. Then there's a whole host of potential applications in manufacturing at the nanoscale. Here, these are shapes, topologies that have been created after de-wetting of a melted substance from a surface. And there's also many kind of classic instabilities that you can use to create nanoscale features. So for example, this shows that you can use the same kind of Rayleigh-Plateau instability to create drops from almost a micron down to tens of nanometers. And so these are the kinds of processes I'm going to be thinking about. And the underlying flows in those kinds of processes are things we recognize from macroscopic flows we know a lot about. So for example, coalescence. This one comes with music. The breakup of thin films on solids and subsequent kind of pattern formation which can occur, and the breakup of jets into drops. So kind of fundamentally from a modeling perspective, these are flows which have attracted a lot of interest over the last 20 years or so because they exhibit finite time singularities. And that was kind of our initial motivation for looking at those. But as you'll see later, the work went in a different direction. So you might ask, well, what on earth are we bothering doing this when we can actually see exactly what's going on here with these processes? And the point is that these are on millimeter scales and we can't see nanoflows. So it's kind of a more subtle point than that. We can actually see things on the nanoscale, but in general, we can't resolve the time scales and the space scales involved simultaneously. So that motivates developing models and computations to look at these kinds of processes because simply there's no other way to do so. I should say, feel free to ask questions through the talk. I'm happy to take questions as I go along. So the kind of traditional tool of choice at the nanoscale would be molecular dynamics. This is not an area I'm an expert in, but I'm going to briefly describe the idea of molecular dynamics because it's conceptually relatively simple. And the idea is you just essentially move particles according to Newton's second law. So you have forces acting upon them, which move the particles. And this force is the gradient of some potential. And typically that potential depends on the distance between the particles. Okay, and that's combined with some appropriate thermostat, and there's subtleties involved there. So if we have an array of particles, we pick one, typically we only think about its nearest neighbors for computational tractability. And the force on that depends on where the neighbors are and the form of this potential. And the most common potential, the simplest, if you like, is the Leonard-Jones potential. So that has two components, a short range repulsion. So it says that atoms should distance themselves from each other, and a long range attraction. So atoms need to distance each other, but not by too far because they attract each other long range. And so in common terminology, I see atoms are the ultimate social distancers, and they remind me a little bit of this woman. I hope you can hear the sound. She's extremely sensible because she's distancing herself in these dangerous times, but also you can see quite sociable in that she wants to go shopping.
Excuse me, love. Really germophobic and doesn't want to see. Doesn't want to see. Are you seriously? No, 2 meters, please. Honestly. No, I'm keeping the 2 meters, but seriously, mate.
Okay. So we use open source software, lamps, and usually the simplest kind of system we can think of, sometimes more complex. And molecular dynamics essentially gives us everything you'd ever need. So out of it comes all the properties we know about, like viscosity and surface tension, thermal fluctuations. But these models are incredibly computationally intensive. So to give you an example, this is two 20 nanometer water drops coalescing. And this is the kind of simulation which has to be run on the national supercomputer. Okay, so the approach we're going to use is we're going to think of MD as an experiment with which we can probe this nanoscale type behavior. But what we want to do is develop models that go beyond classical fluid dynamics. So they have all the niceness that we know how to solve the Navier-Stokes, we know how to analyze it, but there's something extra. So crudely think Navier-Stokes plus some nano stuff. And that's been our approach really for both liquids and gases. But today I'm going to describe the stuff about liquids mainly. Okay, so I'm going to talk about thermal fluctuations in free surface nanoflows. So it's kind of interesting how this project started. The original interest was these two processes, the coalescence of drops and the breakup of jets. They both have singularities when you look at the classical models. And what I wanted to do was just focus MD on these things and see what happens, because when we do molecular dynamics, we don't expect to see infinite pressures and infinite velocities. And so we're interested in what is the kind of missing physics in the macroscopic models. But what I'm going to show you is essentially the research took a completely different direction, and that's more interesting, if you like, or more relevant. So these were the two PhD projects. Sri Hari was in Edinburgh and Cheng Shi was in Warwick. And they just took the kind of canonical flow configurations, two spheres coalescing, a cylinder breaking up to drops, and looked at what happened in molecular dynamics. So with coalescence, the first problem we had was I would say to Sri Hari, well, we're interested in singularities, so just find the point at which these drops coalesce, start measuring things and see what happens. And he'd say to me, well, that's really nice. You tell me, you know, two spheres, you push them together, they meet along their line of approach, but that's not what happens. I'd say, okay. So he would find that the contacts would almost invariably be off center. And that was completely unexpected for a start. And in fact, you would often get multiple contacts, all of which were off center. So this is kind of obvious when you look at a drop, a nanodrop, and it occurs because you have waves propagating around the surface of this drop, which are associated with the thermal fluctuations in the fluid. And so if I stop, just take an instantaneous snapshot of the free surface shape, it's not a circle or a sphere. And then it's immediately obvious why if I push these two shapes together, they're not going to necessarily join across their lines of, along their lines of center. If I average these shapes over time, then I recover the circle as I'd expect. So qualitatively, there were some interesting things here that we didn't understand. Nanojets, similarly, when you look at a macroscopic experiment, you typically see the structure of two drops joined by a thread in between, a satellite drop. If you look in molecular dynamics around the same regimes, you see this completely different structure, which is known as a double cone. Okay, looks like a double cone. And this was discovered by Mosler and Landman in 2000, and they postulated this was due to thermal fluctuations in the fluid, changing the characteristics of the breakup. Okay, so what we saw there was that these nanowaves created by thermal fluctuations are really, really important. And the obvious question is, how can we see these? So as I see it, there are three options that I know about. The first one is that you use incredibly high viscosity fluids, And what that does is it basically slows down the dynamics so that you can resolve it in real time using something like AFM. So this is exactly what people have done. This shows de-wetting of, I think, a polymer film from a surface. It's such high viscosity that it actually de-wets on the scale of seconds, even though it's only a few nanometers thick. So that's one possibility for seeing this kind of thing. Another possibility is that you look at these fluids developed by Dirk Arts and Daniel Bonn and collaborators. They are colloid polymer mixtures which have incredibly low surface tension. And what that means is that the scale of the fluctuations enters the range in which you can use optical techniques. Okay, so you can actually visualize now the fluctuations on interfaces. And then the third option, which is the one we'll follow, is that we use molecular dynamics. And here you can also pick out the wavy type structure on surfaces. Okay. So three possibilities, all with their own real drawbacks. Experiments only really work for ultra viscous fluids. Colloid polymer mixtures are nice, but they're often difficult to focus on all the regimes we're interested in. And molecular dynamics is great, except for we can only do things which are smaller than about 10 nanometers for times less than about 100 nanoseconds, and for simple liquids. So it really motivates the development of theory, what you might say in the spirit of Navier-Stokes, that incorporates thermal fluctuations. Okay, so to give some kind of understanding, I'd like to start talking about thermal equilibrium and then move on to dynamics afterwards. So a lot has been done in this field over the last 100 years. Thermal fluctuations everyone knows about, first of all, through Brownian motion, and a lot of work was done in the earliest 20th century by very famous names. And in terms of nanowaves at interfaces, around the same time, it seems that Smoluchowski realized that thermal motion should create nanowaves. And there's a paper by Mandelstam in 1913 where he derives their properties. And essentially, I'm going to kind of repeat that derivation to give you some kind of insight into these processes. So for lots of the talk, I'm going to be interested in a two-dimensional system. So in terms of our MD, that essentially means it's into the page is rather thin and we average over it. And so we end up with the height of an interface, which is a function of distance along it and time. And in our MD, we take some length for that thin film, and we apply periodic boundary conditions at either end. So we can think of the height as being some average height plus a perturbation. And it makes sense to expand that in a Fourier series. And then the name of the game is to try to work out what these ANs and BNs are, which are going to change in time, or in reality, work out their statistical properties. So surfaces have tension, we know, so that creating new area costs energy. And the energy is very easy to work out. It's simply the distance along this curve, which is essentially the integral of ds here, times the distance into the page times the surface tension, minus, so this is the extra energy in creating area, minus the original energy from the flat interface. If we note that this is small, then we can Taylor expand. We simply substitute that into there, and we find the energy associated with each of these modes. So n is like a wave number here, essentially. Okay. Then we note that in thermal equilibrium, we should expect the average of each of these. So this is steady. We expect the time average and the ensemble average to be the same. So they're given by these brackets here, and equal to KT over 2. And if we do that, we can find the average of the square of these coefficients given by this expression here. Okay, nothing new here, but it's nice to go through it to explain. Okay, so what do we see? We see, for example, that clearly the amplitude is largest for the smallest n, which corresponds to the longest waves. And this LT here has the expression, can I minimize this? I don't know if I can. Anyway, This is KT over the surface tension, and this gives a length scale associated with these waves because it's KT, which is essentially trying to push the interface in all directions, and surface tension, which is trying to pull it back to flat. And so for something like water, this is about 0.2 nanometers and explains why it's a kind of nanoscale phenomenon. So what we're going to be interested in throughout the talk is the spectrum, which has this mathematical form. So you take the Fourier transform, modulus squared, average square root. But essentially, we can think of it as telling us about how waves with some wave number k grow or shrink in time. So what we've just figured out is that in equilibrium, we have this expression. So it goes like 1 over the wave number. And so what I'm going to do now, so I should say this is known as capillary wave theory. There are, what I'm going to do now is I'm going to take this molecular dynamics simulation. I'm going to set it running from something which is roughly flat and see if we approach this expression as thermal equilibrium is approached. Okay, so this is ensemble averaged MD, and we see it grows in time and approaches this 1 over K type equilibrium spectrum. What we're going to be interested in later is actually trying to describe the dynamics of this growth, so how all of these waves grow and how they approach this equilibrium state, or how they approach some non-equilibrium state. Okay, so once we have the expressions we need, we can calculate other things very easily. For example, we can calculate the variance of the interface, just substituting in what we know about an squared and bn squared into here. And we find the following expression. So what we find is that this, the length scale essentially associated with this roughness of the interface increases as we increase the length of the domain. And that's probably what this is kind of intuitive, because the longer the domain is, the more waves we can fit in, the more longer waves we can fit in. Okay, and the same approach in 3D would give us this expression, which is interesting because we now have to introduce a cutoff associated with the smallest scales in the system. So that could be, you could think of maybe the size of a molecule or something more complicated like the correlations within the liquid. Okay, so for our work on drop coalescence, we've only really considered thermal equilibrium, and that gives us essentially what we need to understand why drops coalesce off center. So the qualitative explanation is what Sri-Hari, so can I move this? It's really annoying. Dimitrios, can you see this? Can you see me and yourself and all these things in this corner?
I was muted. Yes, I can. Yeah, we can see it.
I don't know how to move it, which is pretty annoying, but never mind. So what Sri-Hari had worked out was that thermally driven nanowaves are what create this off-center coalescence. But there's obviously a distribution and a length scale associated with where this coalescence can occur. And we had no real quantitative theory for understanding that. So what Makita worked on was looking at both spheres and cylinders. And the reason we looked at cylinders is many of the molecular dynamics calculations were done with thin disks because they're a lot computationally cheaper, and essentially calculated the variance associated with those shapes. So this one comes relatively simple. It's rather obvious. This one, I think, is a new result. Okay, so you can compare that to the molecular dynamics and you see that you have the right variance for the cylinder, and then you can start looking at the sphere with the theory rather than having to use the MD, which is very, very expensive. Okay, so our arguments were rather simple here. What we said was that for coalescence to occur, we need the size of the fluctuations to be comparable to the height between the drops. We know the typical height between the drops because they're just circles, so locally they're parabolic. And we now know the typical size of the fluctuations from the variance. And so we just essentially equate those two things and figure out the length scale over which coalescence might occur. Okay, so we did that, and we find the length scale is approximately equal to the square root of LT, this parameter I showed you earlier, times the radius of the drops. What's kind of interesting is that if we take drops that are a millimeter in size, then this scale can reach microns or even a little bit larger. And so you start to reach the scales which are actually relatively macroscopic and which you might hope experiments can be done on. And this just shows that the MD distribution agrees with this theory. Okay, so the latest stage we've been thinking about, which was a fourth year project last year in Warwick, was to actually look at the spherical harmonics on a sphere, essentially write down SDEs for how each of these relaxes when driven by noise, and then actually look at a nanodrop with fluctuations on driven by the models. And then we can push two of these together and look at the coalescence statistics in a little bit more detail. Okay, so this is just to say that similar things have been seen in the colloid polymer mixtures. You have symmetry breaking there, but you can see this process is very different because it's much, much more like a liquid-liquid system where you have this intervening film which slows the whole thing down. So this is some possibility for the future. Okay, so that's gives a kind of summary of the work in equilibrium. Now let me talk a bit more about dynamics. Obviously, we need equations of motion, and those are provided by the theory proposed by Landau and Lifshitz. So if we think about incompressible liquids, which is reasonable for what we're interested in, then we have the Navier-Stokes equations, which are these first terms here. And all they propose is adding a fluctuating force in the form of a stress with the following form given here. So the average of each of these components is 0, and their correlation looks like this. So essentially this here is the form of the tensor you require. These are Kronecker deltas. This simply says everything's uncorrelated in space and time, and then this is just the prefactor to satisfy fluctuation dissipation theorem. Okay, and so this is the model which we're going to be investigating. You can imagine that even in 3D, Navier-Stokes is pretty nasty. So when we come to calculating something which is stochastic, we now need to kind of manage our expectations, or I need to manage your expectations. Maybe that's what I should be doing. So just to note that we're interested in 2D Cartesian. So we average into the page. That means averaging over the delta function in the y direction, which gives a 1 over Ly and this form here. Okay, so fluctuating hydrodynamics is an area of increasing interest for a number of different applications where thermal fluctuations are important, but you really don't want to be using some molecular model. So things like chemical reactions, this is a mixing simulation, biological membranes, and interfaces we're going to be looking at. Okay, so what we're going to look at is stochastic lubrication equations. So we're going to simplify matters even further by thinking about a long, thin film and the simplifications that can come with that. So we have 2D thin film problem, and I just write down the full problem formulation here. We use asymptotics in the usual way you would for the thin film equation. And the only difference from what you see classically is these two new fluctuating shear stress terms. Okay, so they come into the x momentum in the equation here and into the shear stress boundary condition here. Okay, then we apply our usual approach. We integrate over the film. We substitute in to kinematic equation, apply the boundary conditions, do some fiddling around, and essentially we come out with this. So classically, we would have this dH dt, this term here with the mobility given by h cubed over 3 for no slip, and the pressure given by the surface tension term. Okay, but now we have this nasty integral over the layer, which includes the shear stress term, this fluctuating shear stress term. So one of the really important steps here was by Grun, who showed that this is equivalent to a much simpler form where the noise appears explicitly now rather than under the integral. And I've just taken all of the prefactor out here And so my noise is now just white noise with mean 0 and variance 1. Okay, so this is now something that we can start to look at and analyze. And just to point out, there's a number of people who've subsequently worked on this, including this paper here with Imperial authors, which is a really nice addition to the literature. Okay, so the first obvious thing to look at is the stability of the thin film and think about what changes when we have fluctuating terms. So we take our SLE, which looks like this. We consider linear stability as we always would, some height plus a perturbation. We go into Fourier space and we end up with a nice looking PDE like this. Okay, so this part here would be what we'd see deterministically, and we have omega here is purely negative, so all of these modes we expect to decay, and this is the forcing due to noise. And we can, because it's linear, we can decompose the solution into a deterministic and a fluctuating part. This is the deterministic part, which is easy, and the fluctuating part is also relatively easy. And from those, we can find out the spectrum. Okay, and this was first derived by Mecker and Rauscher in 2005. So the spectrum has this form. And so to compare to what we had before, we now have dynamics. So we have T appearing, we have dynamic variables like viscosity appearing. And if we took T tends to infinity, omega is negative, and we'd recover the equilibrium spectrum. So this is what I showed you before. The MD I showed you before is this data here. This is now the result of this theory over here. And you can see as time progresses, well, I could tell you this is good agreement or bad agreement. You can choose yourself, but I'm going to tell you it's okay-ish and that we want to improve it because that goes along better with my narrative. So interesting thing to note is that fastest growing mode here changes in time, which is a non-classical effect. And the agreement isn't great. So I'm going to do a couple of things to improve the agreement, which are interesting and new. The first thing is to consider slip between the liquid and the solid, because when we have nanoscale flows and when we look at molecular dynamics at perfectly smooth surfaces, it's definitely the case that we have slip. This isn't just some kind of ad hoc addition. And we can measure this slip length in some separate simulations easily enough. So if we do that, it looks simple, but the derivation is actually quite long. We find that the mobility changes from h cubed over 3 to have an additional contribution like this. So if we put that in, that was no slip, which I just showed you, and slip starts to look a lot better. Okay, but we can still look at this and say, well, that's a bit annoying. This doesn't seem quite right at early times. And if we look, we see that the problem occurs around wave numbers, which are around 1. And that's because we shouldn't expect lubrication model to be particularly accurate there. It's a model which is typically only accurate for long wavelengths and short wave numbers. Okay, so that's why it gets better in time. So in a minute, I'm going to show you a Stokes flow analysis for this kind of area. So I guess the most interesting question is, what do fluctuations do in terms of the stability of the film? Now, if we don't have disjoining pressure, then everything just appears to be stable in all cases, which is a bit boring. So typically, to induce rupture, people add a disjoining pressure, which looks like this. So this h cubed over 3 is the typical form. And if we do that, we find that our growth rate can now be negative or positive. Okay, so disjoining pressure enhances breakup and rupture. So if we look at when this is 0, that gives us a critical wave number beneath which we can have instability. So that's a wavelength above which we have instability. So what we should expect if we do an experiment in MD is that if we have sufficiently long domains, sufficiently longer than this critical wavelength, we should see breakup. And if we're shorter than it, we can't fit the critical wave in, and so it should be stable. So let's take a stable case. This is one which is a lot less than the critical wave number, but we find rupture. So here you see, you'll have to trust me, there's another part to this which shows rupture. And the reason is that the arguments I've made say nothing about the fluctuations in the system, and the fluctuations are really important when it comes to rupture. So a different argument is that we can say, let's consider unstable modes to be ones where the spectrum is growing. And so that's actually now going to define our critical wave number at the point where we go from growing to shrinking waves, growing to shrinking spectrum, sorry. And if we do that, we have that the new critical wave number is the old one plus a bit, which depends on the fluctuations. Okay, and what we see, in fact, is that this, for these kind of systems, predicts a much, much shorter wavelength for instability. And that's why in these kinds of systems, we see instability almost all the time in the right systems. Okay, so this is actually a fluctuation dominated regime where this part, the fluctuations, dominate over the disjoining pressure for the early stages of instability. So as I mentioned, the wave number changes in time, which is a non-classical effect. We can extract from the model how it should change in time by this definition. So it should go to t to the minus quarter. And if we look at the MD, we see indeed this decay. And this again comes back to what I mentioned earlier. With what we always see is that at early times, very short wavelengths are excited by the noise, and that these invalidate the lubrication approximation we're making. Okay, so this again calls into question lubrication and again motivates a Stokes flow analysis. So beyond lubrication. So Yixin had the really good idea of, instead of going from the SLE to the kind of model I showed you, let's instead just start with a Langevin equation for the perturbation in Fourier space. So typically for both the lubrication equation and Stokes flow, we have this kind of relation between this perturbation and the growth rate. And now we just basically add noise in the Langevin type way to the right-hand side, which we can derive for the stochastic models, but not directly from fluctuating hydrodynamics for Stokes flow. Okay, so this now, we know omega from the deterministic models for Stokes flow. We can just plug it in there. We know what beta should be in equilibrium, so we can fix that. And so using this model, we can now actually get Stokes flow results. And you see, importantly, that this is able to capture this early time behavior. Okay, and the later times agreed fine anyway. So Stokes flow seems to be important because the noise drives these short wavelength modes. This is even more dramatically seen when we look at the breakup on an annulus, breakup on a cylinder of an annular part of liquid. So this breaks into beads. Again, we can measure the interface and look at its Fourier modes. And there we see quite strongly, this is the MD, and this is the stochastic lubrication model. So you see the lubrication model here flies out the top and doesn't agree with the MD. If we use the Langevin type model, which I've just described, which has the Stokes flow built into it, we can agree quite nicely with the MD. Okay, and so this just basically shows the reason is that the growth rate of the lubrication model deviates from the Stokes model for moderate wave numbers, as we'd expect. Okay, so the last part of the thin film stuff, which was again driven by Yixin, is to look at the roughening of the interface, which is a kind of obvious thing to do and a classical thing to do. So this is the roughness of the interface, which is simply its standard deviation. So this is the h squared average square rooted. And what we want to do is we want to look at power laws and putting this into the framework of universality classes. So what we can show is that the roughness goes, so this is now for the lubrication model where we can do things analytically. We can show that the roughness goes like some power of t before it saturates at some value at some time. The saturation depends on the length, which I've already shown you, and the time, which are the time depends on the length, some powers. And that puts us in a universality class with these constants, which seem uncommon. So just to convince you, this is now MD data for the roughness compared to the power law of T to the 1/8 with the roughness saturating up here. The lines here are for the Langevin model, which is better, but we can't extract these parameters exactly for that model. And we see for early times, the growth looks really good. For later times, you'll notice here, there's no MD data. And that's because the timescales here are just impossible in MD. But we have no reason to believe that these shouldn't follow onto the correct saturation. So it's an interesting point, actually, that to saturate the interface, to saturate the roughness, you actually need times which can't even be accessed in MD. So what we'd really like to do is connect all this to experiments. And there is some possibility you could do that with these ultra viscous films, which has kind of been done before. So in this paper here in 2007, they look at the roughness growth of a thin film before it ruptures. And what they use is arguments associated with the lubrication equation with no slip. And they show that actually that agrees pretty well with the data. And we see the same agreement with the Langevin model. So it's slightly disappointing in some sense that the two agree so nicely for this experimental case, because we might hope the Langevin model gives us more. We might also hope that no slip isn't valid. But what's interesting is that for these polymer films, we often see huge slip lengths are reported in the literature. And if we look at much larger slip lengths, the ones which are often reported for these kinds of films, we start to see completely different growth with deviations between stochastic lubrication and the Stokes flow type model. So there's essentially open problems there and a nice opportunity to connect to experiments, hopefully. Okay, so where this all started was actually by looking at cylinders, but it made sense to talk about the planar case first because Cartesian coordinates are easier than cylindrical coordinates, essentially. So this was Chengxi's project. And so the setup, as I said, is the same as before. We now have some height, which is a radius with a perturbation, a function of the axial direction z. And it was Moser and Landman who first derived the stochastic equations for this case in a famous paper in Nature. And essentially, they're the same as the deterministic stochastic lubrication equations, except for there's a new noise term. Okay, slightly different system because we can't write it as one PDE anymore. We have to write it as a system of two with height and velocity, but conceptually very similar. So what Moser and Landman showed was that, in fact, MD will never agree with the deterministic model, but if noise is added, you can see nice agreement in selected realizations. What's really interesting, though, is that they never considered the instability of this process. So classically, we know what the instability looks like very well. It's the Rayleigh-Plateau instability. And we know that that tells us that two kind of important pieces of information. Firstly, we should only expect long wavelengths to be unstable. That's short wave numbers. And secondly, we should be able to predict the fastest growing mode, and that for a given system, that is just a constant. So what Duncan did was actually do the lubrication, do the instability analysis for the stochastic lubrication equations for the first time. And it follows a very similar process to the one I showed you before. So I'm not going to go through it. I'm just going to say that as a result of this, we find the spectrum as a function of K and T analytically. Okay, so there's these expressions here. So then what we want to do is we take a long cylinder in our molecular dynamics and we simply watch it break up, measure the free surface, look at the spectrum and how it grows, and compare it to our theory. So this is the spectrum in the MD, the maximum wave number does change in time, but it's not so dramatic here. And this is the deterministic model. So it's remarkable how bad the deterministic model is here. And it's essentially because these nanowaves really enhance the early stages of instability. So if we use the new theory, the agreement is remarkably good, and there's absolutely nothing to fit here. So this was a JFM Rapids last year, and I was super chuffed that Chengxi produced some artwork for the front page. So chuffed, I sent him an email saying, "Hey, Chengxi, Duncan, this is pretty cool." Sent them the picture, like the sad individual I am. Duncan replied with the correct level of enthusiasm. "Amazing, we're famous." Chengxi, glad to see it. So I thought, well, that's not acceptable. So I said, you're not sufficiently excited. This is the highlight of my research career. Chengxi replies, "I should have added an exclamation mark to his sentence to express my feeling." So you can see here clearly, Chengxi, the PhD student, is the real scientist, and Duncan and I are just seeking fame and fortune wherever we can get it. Okay, so as before, we find that short wavelengths become more important when we have thermal fluctuations, and the result is that we can rupture things which are classically stable. So this is a fat cylinder which should be stable, but you'll see we have essentially the perfect storm of fluctuations that can eventually rupture this. And what we looked at was how long does it take on average for these things to break that are stable? And what you see is the more stable, the fatter these become, the longer it takes. And you have this nice curve which we produced, and we have no idea how to calculate it analytically. So I spent some time in the summer thinking about this, and I made almost no progress. So that's a nice kind of open problem we have. Okay, so I've only actually really mentioned how we look at analytic work with the instability. We haven't talked really about the breakup and the nonlinearities involved, which are really, really interesting. So let's do that now. So obviously we now need to solve the SLEs computationally somehow, and we need to think about this nasty noise term. So the simplest thing we thought of, not really being from this background, was just to, on each of the nodes, we put some random numbers with the right variance. And in fact, that works very, very nicely for the linear stage. It gives us nice results which agree with the spectrum. So this now shows our stochastic computations. On the other hand, when we get to the nonlinear stage, the whole thing is a total disaster, and we lose all notions of convergence under refinement of grid and time and all these kinds of things. So this is not a surprise for anyone who knows about these kinds of stochastic PDEs. What we chose to do was semi-physically motivated. The idea really is that in the liquid, there are correlations, and that those correlations might come to our rescue. So both spatially and temporally, there are correlations within the liquid. We can measure those in MD, and we can extract numbers which are finite. And then we can either do something crude, such as just interpolate within these correlation scales, or project onto an appropriate basis, which is really the right thing to do. And if we do that, we can indeed see convergence as we refine the mesh underneath these correlation scales. So this now shows the breakup shapes we see, and the breakup shapes agree quite nicely with the MD. Okay, so we can now run for both macroscopic breakup and stochastic nanoscale breakup. This is obviously nanoscale with the waves and the fluctuations traveling along. It's now a stochastic process, so it differs every time, but it typically occurs quicker than the deterministic case, and the shapes are very different. We have here two drops connected with a drop in the middle, breakup occurring here and here. Looks like the macroscopic experiment. And in the nano case, we have this double cone structure, which you see in the MD. So we were quite happy with this. And now, of course, we can compute across scales from nanometers, microns to millimeters, look at the experiments in these cases. This stochastic type approach is 5,000 times faster than the MD at the nanoscale. And of course, you can't do MD at anything but the nanoscale. Okay, so there are similarity solutions which have been proposed for the breakup. There's two particularly famous ones, one by Eggers in '93, which considers the balance of viscosity, inertia, and capillarity, and then one by Dimitrios in '95, which is the balance of viscosity and capillarity. And they are well known to produce different kind of shapes. But of course, now what we're really interested in is what happens when we have fluctuations as well. Well, believe it or not, there's actually a similarity solution in that case as well, proposed by Eggers. And essentially what he considered is the most probable breakup shape in the noise-dominated regime. Noise-dominated basically means that surface tension is neglected. And importantly, you see this symmetric shape reappearing. And you have a power law for the breakup, which goes like 0.4. And there's been some kind of verification, although qualitative rather than quantitative, from the colloid polymer mixtures I showed you earlier. So we can now focus our stochastic lubrication equation on this process. And what we see is, in terms of the power law, we can approach this power law as we reduce our surface tension to what is going towards unphysically small surface tensions. But nevertheless, the surface tension, when the surface tension is neglected, essentially, we can go towards the right power law of 0.4. Unfortunately, or interestingly perhaps, the breakup profiles don't agree. So it's clear that there is scope here for a new improved similarity solution building on these kind of really interesting techniques which Eggers used in this paper, but perhaps incorporating surface tension as well. So just to show you, we can then see transitions between different regimes. This is the breakup, the width of the film, the width of the jet essentially. And you see, for example, we start off in this viscous regime as predicted by Dimitrios, and then you transition at smaller scales to a fluctuating regime given by the power law proposed by Eggers. Okay, so what does time permit? So I said if time permits, I'll overview our work on gas nanoflows, and looking at the time, it doesn't really permit, and that's exactly what I expected. So I'm just going to literally put up some references here. Apparently this is on YouTube, so you can watch this back at your own leisure, and just mention one of those applications because it's a recent one. And that is, so I should point out this is a completely different project, although there are some relations. That is looking at drops impacting solid surfaces and ultra smooth solid surfaces where you can see bouncing due to gas films underneath drops. So what we're interested in here really is at what impact speed does this drop break the gas film underneath and wet the solid? And what you find is that these films go down to tens of hundreds of nanometers, and you need to use gas kinetic theory in there. And that's essentially what this paper is all about. So I can show you a simulation from our work, but that shouldn't really convince you that everything works. It should just show you that roughly when the drop doesn't touch, we get the right kind of agreement. But the real test for a theory is whether it predicts the transition between bouncing and wetting. And indeed, we can predict that nicely. The conventional model without gas kinetic effects predicts the transition at 2 meters per second, and our model is around 0.74 as hoped. And finally, to say we can then do kind of virtual experiments in a vacuum chamber, which haven't been done yet, but would be of interest. And we see classical model is miles away from this transition. And we see very different modes of breakup depending on the regime. But these modes are always driven by van der Waals forces. So here you see instability of the film driven by waves coming from van der Waals forces. So again, it's a really interesting process where we have both gas kinetic effects and van der Waals forces acting on this film. And only with both can we really describe what seem like quite innocuous experiments. Okay, so finally, a pre-social distancing photo of our group. I've already mentioned the appropriate people, the appropriate funders are down here, and I'd be happy to take any questions you might have.
Great, thank you very much, James. So we're ready to take questions. Does anyone have